everybody. Welcome to the lecture series on analog communications. By this time we might have got good knowledge about what are the different analog modulation techniques, particularly continuous wave modulation techniques. We know the broad category of modulation classification. Fundamentally, we have classified the modulations into analog modulation techniques and digital modulation techniques. This classification is based on whether message is analog or digital. Okay. So again, analog modulation techniques are further classified into two types. One is continuous wave modulation and pulse modulation. In continuous wave modulation, the carrier is a sinusoidal. You can use cos omega CT or sin omega CT. In pulse modulation, the carrier is a periodic pulse waveform. Basically, if I categorize, then continuous wave modulation techniques, we have broad classification into amplitude modulation techniques and angle modulation techniques based on the parameter varied. In amplitude modulation techniques, amplitude vary. In angle modulation techniques, angle vary. Okay. Further, as their objective is to save the power, save the bandwidth, amplitude modulation techniques are broadly divided into four: double sideband full carrier AM, double sideband suppressor carrier AM, single sideband suppressor carrier AM, and vestigial sideband suppressor carrier AM. These are the four categories coming under amplitude modulation. Already you might have been familiar by this time. Why? Because once you are entering into pulse modulation techniques, you might have some idea about what are the different continuous wave modulation techniques. Among all the four amplitude modulation techniques, if the power and bandwidth are considered, single sideband suppressor KR modulation is good. But however, the noise performance of these modulation techniques is poor. Amplitude modulation techniques are easily affected by noise. That is why we have gone to angle modulation, right? In angle modulation, frequency modulation and phase modulations are the sub-techniques. Why? Because now so many modulation techniques are depending on which parameter is varied. We have defined in the beginning of our lecture series. Modulation is defined as the process of changing some parameter of a carrier signal, in particular, which is a high frequency signal. Modulation is defined as the process of changing some parameter of a high frequency signal called as carrier signal in accordance with the instantaneous value of the message signal. The definition is known. Being a communication engineer, the definition of modulation must be familiar for everybody. Now question comes, when so many continuous wave modulation techniques are existing, why pulse modulation? Before I elaborate why pulse modulation, let us know what is the reason for going, what is definition of pulse modulation. Pulse modulation is defined as the process of changing some parameter of a periodic pulse waveform in accordance with the instantaneous value of the message signal. In pulse modulation, we are not going to use high frequency signals. That is why pulse modulation techniques are coming under a series of a category of baseband modulation techniques. Baseband means modulation is performed at relatively low frequency. Okay, why we are performing baseband modulation? Why pulse modulation if it is low frequency? A little ambiguity generally. People may say modulation is done to reduce the size of the antenna. So modulation requires high frequency carrier signal. But pulse modulation is baseband. What is this means? Fundamentally, there are few advantages. Pulse modulation is required to make use of the Advantages of digital IC technology. This is the first and foremost advantage. Why? Because ICs, digital ICs are flexible, they are programmable, and they are accurate. They are, of course, low cost and they are simple. Totally five advantages of digital technology. What are they? Flexible, programmable, accurate, simple, and low cost. When digital technologies are having so many advantages, why we should run behind the analog techniques like AM and angle modulation is the fundamental question. So, as digital technologies are having advantages, we have to shift over to them. Okay, but your signal is analog, right? Your signal is analog. It is a continuous wave. Then how to use digital technologies for this is sampling. Sampling is the fundamental technique in communication which is going to convert a continuous time signal to discrete time signal. By definition, no? Sampling is the process of converting continuous time to discrete time. Why? Discrete time signals are occupying less storage space, lesser bandwidth, less processing time, and less transmission time. Discrete time signals, no. Why? Because we know what is the difference between a continuous time signal and discrete time signal. We all know. Very familiar. But for your information, what I do, I just give an illustration. Okay. Digital IC technologies are going to be having number of advantages. So in this context, we need to make use of them. Have a glance. Let me just sketch here. Okay, this is the continuous signal. Okay, a continuous time signal. X-axis is always a time and y-axis is the amplitude known to us. However, can we count the number of values in this? Never. Infinite number of values. Those who are familiar with switching theory and logical design, if there exists infinite number of levels or values, definitely I need large number of bits. For 8 levels, 3 bits, 16 levels, 4 bits, right? So here infinite possible amplitudes. So there exists infinite number of bits to store this and making the processing also complex. So that is why what we do, instead of taking every value, we are going to select few values called as samples from this signal, that is a continuous time signal, and transmit them or process them for the requirement to be satisfied, right? See, and of course, the number of samples that have been taken must be able to reconstruct the original message signal. Whatever signal you are sampling, after processing, it must be reconstructed back. Then how you will define number of samples required? That is defined by using sampling theorem, which states for efficient representation and reconstruction, the number of samples should be twice the highest message frequency. That is, Fs must be greater than or equals to 2W, right? Okay. Fs is the sampling rate. Must be greater than or equal to 2 into W. W is the highest message frequency. So sampling theorem defines the condition for efficient reconstruction of the original message signal. So sampling is the fundamental tool for converting continuous time to discrete time, which enables the use of digital technologies. Okay. Now let us come back again to our discussion. What we are talking about? We are talking about your pulse modulation techniques, right? Okay. What do we have defined? Pulse modulation is defined as the process of changing some parameter of a periodic pulse waveform in accordance with the message signal. Now, what parameters pulse may have? Generally, pulses have amplitude, pulses have time. So you can classify the pulse amplitude modulation techniques into pulse amplitude modulation and pulse time modulation. Okay, why? Because a pulse, should I just go back our discussion one more time to effectively tell you that? Okay, let me just draw a pulse waveform here. One second. Let we take a pulse and then demonstrate what are the parameters that a pulse can be varied. Pulse amplitude can be changed. Okay, pulse time can be changed. If I define on time, pulse amplitude modulation is defined as the process of changing the amplitude of the periodic pulse waveform in accordance with the message signal, PAM in short. PTM, pulse time modulation, is defined as the process of changing the timing of the pulses. Have a glance, timing of the pulses, when they are going to occur or how they are going to occur. PTM, pulse time modulation. So if you talk about time, it can be categorized into either width or position. No, okay, the width of the pulses can be varied as well as the location or position of the pulses can be varied. Thus, pulse width modulation is defined as the process of changing the width of the period pulse waveform in accordance with the message signal. Pulse position modulation is defined as the process of changing the position. Position means the location of the spacing between the pulses in accordance with the message signal. Right? Okay. So sampling is the fundamental on the foundation for converting a continuous time signal to discrete time signal. We have discussed already or mentioned already, sampling rate must be greater than or equals to 2W. W is the highest message frequency. Yeah, see these waveforms. The first waveform corresponds to a continuous time signal. Second one corresponds to the carrier signal. The carrier signal in such a case is a periodic pulse waveform. Okay, so in this one, the amplitude is changing. In fourth waveform, the duration or the width is changing. That is why pulse width modulation techniques are also called as pulse duration modulation techniques, PDM. Pulse duration modulation or pulse width modulation are same. Coming to pulse position modulation, the spacing between the pulses is varied. Okay, so yeah, then hope the definition is clear. Now, once we have categorized why pulse modulation, then what are the types of pulse modulation? Pulse modulation is required to make use of the digital IC technology, having number of advantages. The advantages of digital IC technology are: first one, flexible; second one, programmable; third one, accurate; fourth one, simpler; fifth one, low cost. Okay, then classification. Pulse modulation techniques are classified into three types. To be strict enough, analog pulse modulation techniques are classified into three types. One is PAM, pulse amplitude modulation. Second one, PWM, pulse width modulation. Third one, PPM, pulse position modulation. With this foundation in the mind, let us slowly go to PAM. Pulse amplitude modulation is defined as the process of changing the amplitude of the periodic pulse waveform in accordance with the instantaneous value of message signal. What it means? In pulse amplitude modulation, the amplitude changes while width and the position are fixed. Okay, that is definition. So why are you going for PAM? Already we know. Why are you going for pulse modulation? Corresponds to same PAM also. So there exist three ways to generate a PAM signal, pulse amplitude modulated signal. But their root is same. Irrespective of the classification of pulse amplitude modulation techniques, root is same. What is that? Sampling. Sampling is used to convert a continuous time signals to PAM signal, that is pulse amplitude modulated signal. As we have three types of sampling called as instantaneous sampling, natural sampling, and flat tap sampling, we can generate PAM signal, pulse amplitude modulated signal using any one. Okay, so the first one is instantaneous sampling, also called as ideal sampling. Okay, in ideal sampling or instantaneous sampling, a switch is closed for zero time and opened for a time of Ts. Name itself indicates no ideal or instantaneous. What is the meaning of instantaneous? We are going to multiply the message signal with a periodic sequence of impulses. I want to convert, I want to convert a continuous time to discrete time. How to do mathematically? Mathematically, I have to multiply this continuous time signal with a sequence of impulses. From the sampling property of impulse function, we know if you multiply any signal with impulse function, the outcome will be value of the signal at the time instant only. So see this diagram. The switch is open for duration capital Ts and closed for zero time. So what it means, whenever the switch is closed, okay, here closed, value present, here open, value absent, Ts, 2Ts, 3Ts, 4Ts, etc. Switch is open and closed. Open and closed. Closed means output follows the input. Open means output is zero. Undefined. I should not say zero. Undefined. Okay, so if you're asked, hey, explain about natural, generation of PAM using ideal sampling, we need to draw these waveforms. Okay, the other name of this device is called as a switching sampler. A switch, no, opens, closes, opens, closes, opens, closes. However, ideal sampling fundamentally have some drawbacks. What are the drawbacks? It is difficult to have a switch which closes for zero time. No, practical switches are not possible. No, imagine you are switching off a fan. Will it be immediately stopped fan? No, same is the case. This electronic switch, whatever you are using, it may not have zero closing time. So, not possible. Second one, even possible also, the width of the pulses is very, very low. As ideal sampling is going to have almost zero width pulses, power content is negligible. So, second drawback is they are not fit for transmission. Third one, right? These pulses are having varying amplitudes. Okay, so the transmitter must be able to withstand the varying powers. These are the drawbacks of ideal sampling. Coming to these mathematical expressions, I mentioned already. We have to x of t message signal. Delta ts of t is the periodic impulse train. They are multiplied in time domain. So multiplication in time domain equals to convolution frequency domain. So this will be the spectrum of the ideally sampled signal, which is practically not possible. That is why we go for natural sampling. Is it clear? There are three techniques for generating a PAM signal: ideal, natural, flat top. We are going for second one, natural. So in natural sampling, the switch is closed for a duration which is non-zero. What is the meaning of non-zero? The output is present for specific time instant. Switch is opened and closed, same process. No much difference is there. But the difference is whatever is the closing of the switch corresponding, that is non-zero. It means output power is going to increase. So this is the message signal M of t or X of t. Notation is our convenience. This is our carrier signal, periodic pulse waveform. No, have you observed in the previous case, bit of the impulses is zero. But in this case, we are making use of a rectangular pulse waveform whose width is non-zero, which is going to result in a signal like this. But question comes, what is the why natural name natural sampling? The name natural sampling is given because the sample signal follows the shape of the original message signal. You can see easily here. Okay, we can easily observe the shape here. As the shape of the pulses is going to be same as the original message signal, like this. Yeah. Yes, see this. The message signal shape is preserved, natural. What is the okay? We have seen previously three drawbacks. No, it is not possible to have a switch which closes for zero time. So that problem is removed. Second one, previous case in ideal sampling, the power is very negligible. But in this case, power is not negligible. Why? Because each pulse is having some width, some duration. I mean, some time, some value, width. Okay. However, the transmitter must handle varying power. That is the drawback. Of course, that is going to stay. Okay, natural. However, one more problem is there. Natural sampling, of course, in natural sampling is practically okay. It is feasible. Why? Because we don't need an ideal switch. But the drawback is output follows the input. What is drawback of this is we cannot discriminate whether the amplitude variations are occurring due to either the message variations or the noise variations. Okay, let us see. Is it clear? The drawback of your pulse natural sampling is it is difficult to discriminate between actual variations or noise variations. Suppose say noise occurs. How can you say whether it is a yeah, 1 second. Let me just show. See, in natural sampling, the shape is preserved. See, the amplitude is following. Now, here some noise occurred. How can we say it's noise? It can be original message signal contribution or noise contribution. That difference we cannot identify in natural sampling. So natural sampling is easily affected by noise. That is why we go for next technique called as a flat top sampling. Hope understood. What we are heading for, we are talking about generation of the PAM signal. A PAM signal can be generally produced by either ideal or natural or flat top. First, to having some drawbacks. What is the drawback of the first one? Practically not possible. Drawback of second one, practically possible but easily affected by noise. That is why you go for the flat top sampling. Flat top sampling is achieved by or a PAM signal is generated by using a technique called as sample and hold circuit. You can see the diagram here. A sample and hold circuit makes use of two switches. This is not a mechanical switches. They are electronic switches. Mostly we use FETs or MOSFETs for faster operation. if we don't know if it has gate, drain, and source, G1, G2 corresponds to gates of the sample switch and discharge switch. These switches are going to open or close periodically to generate a flat top sampled signal. Okay, so how it happens? Let us see what are the ways they can be on or off. How many gates we have? Two, G1 and G2. So initially, what is done? Initially, G1 is on, G2 is off. So what it means, switch 1 is on, switch 2 is off. It means the output is going to follow the input for a given duration, right? How to make on? G1 means gate of transistor 1, no, sampling switch, no. So automatically G1 is giving some excitation, some input on, switch is closed, output follows. G2 is off, switch is open, right? Then second case, what is required? A sample and hold. Our objective is to maintain the amplitude constant. Remember, in natural sampling, the amplitude is changing. So it is easily affected by noise. We don't want that. We want amplitude to be constant. That is the name, no? Flat top sampling. So second condition, G1 off, G2 off. Both the switches are off. Means open. What happened? Whatever voltage previously the capacitor is holding, it is maintained. No, sample and hold. Last condition. Okay, we have taken next sample. No, next condition is G1 off. No change there. And G2 on. Remember, off means switch is open. On means switch is closed. G2 on. These are the three conditions one must remember to generate a flat top sampled PAM signal. Clear? Let's go back to our diagram now. Okay, we see the diagram and proceed further. Yeah, G1 off on, G2 off. G1 off, G2 on, G1 on, G2 off means output. This switch is open. This switch is closed. Output follows. G1 off, G2 off. Whatever voltage this capacitor is charged, it is maintained. Last one. G1 off, G2 on. This switch is on means switch is closed. This voltage is discharged. However, we need to remember the time constant must be small. Discharge time constant or charging time constant. They must be small for effective generation of the PAM signal. So this is how we generate a pulse amplitude modulated signal using three techniques: ideal, natural, or flat top. Which is best? Flat top is best. Why best? As the amplitude is constant, we can easily discriminate between noise variations and message signal variations. And this is the time domain representation of the PAM signal generated through flat top sample. Okay, then generally transmission, any signal for transmitting, it needs a bandwidth. The transmission bandwidth of the PAM signal is larger than the message bandwidth. Okay, W. Okay, then demodulation. It is a process. No, we talk about definition, then generation, then demodulation. So demodulation of PAM signal. Any PAM signal is generated using two circuits. One is a holding circuit, second one is a low pass filter. So how it works? The holding circuit is almost similar to the two switches which we have used in the previous discussion. Whenever, what is the role? A holding circuit is going to take the first PAM pulse. We know what are the pulses previously. The output of the flat top sample signal is PAM. No. So PAM contains number of pulses with varying amplitudes. First pulse is taken. The holding circuit maintains that pulse till next pulse is resigned. How it happens? Let us see here. Okay, come on. Ultimately, we have to reconstruct, right? So let me draw that waveform first of all of the PAM signal and then, okay, yeah, let me draw. So first of all, a flat top sampled PAM, say it is like this, which is obtained through sample and hold circuit. Okay, 1 second. They must have same width, PAM. Okay, so how it works? This is received. Now, the receiver side, the first pulse is received. Okay, switch is closed. First pulse is received. After this, what happens is this value is maintained till the next pulse. Actually, here it has to end. No, it is maintained. Second pulse arrived. Okay, sample is taken again. Here it is maintained. Okay, the duration of the second pulse is over here. Again, next value is taken slightly larger, maintained. Okay, here also maintained and close. So if I simply mention one word, the holding circuit converts the incoming flat top sample signal into a staircase waveform, right? Which is given to a low pass filter. What is a low pass filter? We all know a RC low pass circuit acts as a integrator. So by properly choosing the RC time constant value, the low pass filter smoothens this waveform and generates a continuous signal like this, as we are currently discussing here. Okay, close. Right? So what are the individual roles? Holding circuit converts the incoming flat top sampled PAM signal into staircase waveform. We know what is the meaning of a staircase. Like this. Taken, maintained staircase waveform. And low pass filter, by properly choosing the time constant, it converts into a message signal, which is nothing but, I mean, demodulated signal. The output of the low pass filter is a demodulated signal. This is how we demodulate a PAM signal. However, it has some disadvantages. Okay, it is the fundamental pulse modulation technique. The circuitry required is not at all a complex. And whatever you are generating, that is PAM signal, can be used to generate other modulation techniques also. Advantages, but it has a number of drawbacks. The primary drawback is pulse amplitude modulation requires synchronization pulses. For effective demodulation at the receiver side, we have to send synchronization pulses from transmission side. That's a drawback. Second drawback, the power is not constant. As the power is varying, the device, the transmitter must be able to handle the varying powers. And one more important thing, amplitude is changing. So whatever drawback we have seen earlier in amplitude modulation, same drawback also exists here in PAM, right? So what are the drawbacks? It is easily affected by noise as amplitude is changing. Second one, pulse amplitude modulation requires synchronization pulses to be transmitted along with the required pulses. Bandwidth is also little large. Whatever transmitter that is to be designed must handle varying powers. That is about need for pulse modulation, types of pulse modulation, and generation and demodulation of pulse amplitude modulation techniques. Hope it is clear. Go on learning. In the next lecture, we talk about pulse width modulation in detail. Thank you all.